Yo, what is up, guys? Welcome back. Episode 95, I think. We're going to take a look at our Pokemon of the day. We got an Onyx today. Definitely a classic as well. Let's take a look at the sound. Let's take a look at the voice clips. There's our sound right there. Ooh. Ooh. There we go. So yeah, that's our problem of the day. Let's take a look at count good triplets. Given an array of integers and 3 integers A, B, and C, you need to find the number of good triplets. A triplet A, J, and K is good if the following conditions are true. If 0 is less than I, is less than J, is less than K. Okay. Array I minus array J is less than A. If array J minus array K is less than B. If array I is less than array K, where X denotes the absolute value of X, return the number of good triplets. Interesting. Let's do the brute force solution here, which I think would just be a triple loop. But here we need to start from I plus 1, I plus 1, and I plus 2. You need to find the number of good triplets. Triplet. Good if the following conditions are true. I think we'd start from I plus 2, right? Because we'd want to start from here and loop through each time. Probably want to go to the length of the array minus 2, right? Because the length of the array would be out here, 1. Maybe we want to go minus 3. We probably want to go till here, or else it'll go. I don't know. We'll see. It's good if the following conditions are true. Okay, so. I don't think we need to do this condition, right? Because technically we're already making sure we're doing that in here, right? We're making sure that J is greater and K is greater. So I think what we do here is we just go array I. Array I minus array J is less than or equal to A. So I guess we're looking at the value. But what is A in this case? Given an integer, 3 integers A, B, and C, you need to find the number of good triplets of triplet A, I, J. Oh, we're given A. Oh shit. that's stupid of me. Okay. And array J minus array K. Array I minus array J minus array K. That's less than or equal to B. And array I minus array K then equal to C. Okay, and we would just increment our count by 1. We have our count up here. count is equal to 0 for count, and then we would just want to probably return our count. I think that we're gonna have an index out of bounds error here, I think. No, we don't. 34. How are we getting 34? How are we getting an output of 17? There's not even 17. Why do we have two triplets? 301. They're the same. Loop through all the triples and count the ones that are good. Okay, maybe we have to actually add this if is less than or equal to I is less than J is less than K is less than array dot the length of the array. We check this if we check the count. We got 20 now. We got 10. Oh, we need the absolute value. Okay. And the abs of K. Oh. K. And the abs of there we go. Let's go, dude. Brute force solution. How do we? I'm sure there's a O of N solution here easily. 3 loops gay. What should we look at today? I believe we were looking here, 150 original classical questions. Ooh, we were going to look at that problem yesterday as a tree though. That's what we were going to do. Count prefix and suffix pairs. Right, so there's actually a tree version of this. Reset our code. Prefix suffix pairs 1. Trees are definitely tries. I don't know what to call them. Try. I don't know. Maybe we have to create our node class. Class try node. Self dot map is equal to this. Yes, wait, this would be self dot children is equal to this, and then we do self dot end word is equal to false. Oh, I gotta set my streaks, man. Ugh. Okay. Okay, let's have a look at this question again. You're in the zero index string array words. Let's define a Boolean function. Is prefix after that takes string 1 and string 2. Is prefix and suffix returns true if string 1 is both a prefix and a suffix of string 2 and false otherwise. For example, prefix ABA is true because ABA is a prefix ABA and also a suffix, but is false. Return an integer denoting the number of index pairs ij such that I is less than j and is prefix suffix is true. Okay, so I think we're gonna need some sort of like count maybe or something. Self.count is equal to 0, right? What are we gonna need? So we're gonna need a Reserve 42. Count prefix and suffix. And suffix pairs. Try solution.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem count prefix and suffix pairs 1, and we're actually going to solve the second one in this video as well, because it's the exact same problem, except that one is a Leetcode hard. If you don't believe me, let me just quickly show it to you. It is this problem, again, exactly the same problem, except the constraints are much more strict. And so what we're going to do today is implement two solutions. One is the intended solution for this problem. That is the Leetcode easy. It's going to be a relatively simple brute force solution. And most of you are probably going to be satisfied with that one. But I'm also going to cover than this. Well, given that we're dealing with prefixes and suffixes, you can imagine that a data structure like a prefix tree or a suffix tree is going. I've solved it with a prefix-suffix tree, and I did it with some pretty readable code in my humble opinion. It's actually only about like 30-ish lines of code if I got rid of some of the white space, but it goes down to like 39 lines of code. Most of the complexity is in the try, and the code actually doesn't look that bad. But I want you to know how I came up with the solution, because I didn't come up with it. I went to this problem and I saw it's a pretty hard problem. How could somebody have solved this? I went ahead and looked at the solutions, and then I came across a very familiar profile, Lee, very famous in the Leetcode community. And then I went through and read his Python solution, and all I could think to myself was, holy fuck, no pun intended, because look at this code. But for me, it's actually not that bad, because I don't mention it a lot, but this is actually how I learned how to get good at Leetcode. 7 years ago now, we didn't have video explanations on YouTube. The best we had was, Nick White, I think, at the time, and no disrespect to him, but didn't really explain things super well, so I preferred to just read solutions like these and try to decipher them. So that's exactly what I'm going to spend the rest of this video doing, and very briefly, I'll walk you through this code. In like 30 seconds, I'll tell you what he's actually doing here. I've never seen this before, but he's doing something very creative. He's creating a try. First of all, he's creating an inline function which returns a default dictionary of type T, but he's assigning type T to be this lambda function, and he's using the walrus operator because, of course, he wants to make it as concise as possible. That's classic Lee. And then that function itself, which T is that lambda function, then he's calling that function, and that is the root of the try. And this is only scratching the surface. This is only the first line of code. Then he has the result, pretty much the count, which he's going to return, same thing that I did. Then he's going through every word. X is the root of his try. Then he's going through every character from the beginning and every character from the end simultaneously, and then K is that pair of characters. He's using a pair of characters as the key for his try, again, walrus operator. He's using 0 then as a key, not as like the key of the try, but because his try node clearly does not have a count variable. So he's using 0 to be that count variable, because he knows 0 is never going to be used as an actual key for this, and then the default value will be 0 here, so he doesn't get a random try node returned to it, because that's what a default dict would do. And then he's taking that count and adding it to this, and then after all of that is done, he's marking the end of the word, or the beginning, like the prefix and the suffix at the same time, after having gone through all the characters. And what's probably most confusing about this solution is he's actually not following the semantics of the problem that was given. He's not checking that for a given word starting at I, how many words to the right of it is this word a prefix of those words. He's doing the opposite. He is just to show you how I was trying to decipher his code, so I kind of made some comments for it just to make things readable for myself. This probably may not help you, but specifically, he's not checking if W is a prefix and suffix of the other words, like all the previous words. He's checking if all of the previous words, how many of the previous words are prefixes and suffixes of the current word. He's doing something very clever, and if you don't understand what I just said in the last 2 minutes, that's expected. You're probably human. So I'm going to give you the human explanation of this code, which is up above. So let's get into that. First of all, you have to understand that if we were just checking for prefixes, we could do something very, very trivial. Let's say these are our words, and what we would do is basically, let's say, add all of these to the prefix tree. And I'm not going to go over what a prefix tree is in this video. I don't want it to be an hour long. You can check out my advanced algorithms course if you want to learn that data structure in depth. But let's say we added all of these words, so something like this, A, B, A, and then A, B, A, B, A. So adding 2 more characters, so there's that, and then this one as well would be AA. And then we want to check how many words is this word a prefix of. Well, we would just follow the nodes, and since this is only of length 1, we would only get to this node, and we would check how many times has this node been inserted. It's been inserted 3 times, 1 for this word, and for this word, and for this word. So we would have a count of 3. That would be easy if we were just checking prefixes, but what if we're checking prefixes and suffixes? Well, then things get very complicated. The first thing that you would try is probably create a prefix tree and then create another data structure for the suffix. So the suffix tree. So I don't know necessarily if there is a solution that's actually possible by having 2 different trees, but even if you did it that way, I don't think it would be any more efficient. Theoretically, you could add every single possible suffix for every single word to that data structure, and then it would work, but at that point, the solution wouldn't be super efficient, because then you're not just adding each string once to the suffix tree, you're adding multiple substrings for that tree. So the solution to that is very, very clever. It's to combine both the prefix and the suffix tree in a very clever way. You do associate a count with every single node, but more importantly, the key for that node is not going to be just a single character anymore. It's going to be a pair of characters. That pair is going to be like this. Suppose I want to insert this into my tree. I'm going to have, for the first node, is going to be the first character and the last character. For the second node, it's going to be the second character and the second to last character, which in this case is going to be B. And let me actually, to the try, add this word, because then we'll check if this is a prefix and suffix of this word. So the first node is going to be the same. The second node is still going to be 2 B's. The third word is going to be 2 A's. And then my pointer will be here and here, which is going to be 2 B's. And then my pointer is going to be here and here, which is going to be 2 A's. So this is that combo. Coincidentally, right now, every node has the same characters, but that's not always going to be the case. Imagine if we had a word like ABC, then it would look like this. It would look like AC, and then it would be BB, and then it would be CA. But for this word that we just inserted, now I want to check, is this a prefix and a suffix of that word? Well, I'm going to do the same thing kind of to go along the path. I'm not just going to check A for the first key and then B for the second key and then this for the third key. I'm going to check both at the exact same time, because this, if you were to follow all of these characters, this is this word from left to right. This is the same word in reverse order. So now, if I go through this word pair by pair from left to right and right to left at the same time, I can get this pair, and I do a single comparison, a single lookup to see, okay, the first character matches the first character of this word. The last character matches the last character of this word as well. So far, so good. Now I'm going to check B, and B. So the second character matches the second character, and it matches the second to last character, so this is equal as well. And then finally, I'll be here and over here, and I'll check that yes, this matches the third character and the third to last character as well, and then we'll be down here in the try, and then I'm done. I'm done traversing this word. I find that yes, indeed, it is a prefix and a suffix of this word at the same time, and we're here. So we would return true. But not just that, we would have associated a count with this, because what if it's possible we inserted not just this word, but maybe I inserted this word, A, B, A, B, A, B. And then the count of this node would have been 2, because that tells us that obviously the drawing's getting messy, I apologize, but this word here, ABA, is a prefix and suffix of this word, but it's also a prefix and suffix of this word. Now, this is insanely complicated. I guess, honestly, it's not that complicated when you think about it compared to like Lee's solution, because I'm going to be doing it the intuitive way. I'm going to be doing it such that we are actually iterating over these words in reverse order, because I'm going to add this word to the try. And then I'm going to check, okay, for this word, I'm going to look up in the try, which will tell me how many words is this word a prefix of and suffix of, like all the other words that came to the right of it. And the benefit of this solution is for every single word, we will only need to insert it into the data structure once, so we'll need to scan through the word to do that, and we'll only need to do
This is extremely confusing.
I'm just going to walk you through the code because for the most part, this is a traditional try with some minor changes. So if you've solved any of my other try problems, this should look familiar to you. I have a try node here. I have the children of the node. I also have a count associated with each node. That's going to be important. And then I initialize the try with the root, and that's just going to be a try node, empty. And to add a given word, I start at the root. For the word, I go character by character in the word. This is doing some fancy stuff in Python. Basically, I'm zipping both the word and the reverse of the word at the same time, so I can iterate through both of them at the same time. It's just kind of a convenient thing to do. I didn't have to do it this way, but I think it's pretty readable. So this is character 1. This is from the beginning. This is character 2. This is from the end. And so I create a key. I create a pair using both of those characters, and then I check if that hasn't been inserted into the current node. Then I'm going to insert that using that as the key and then creating an empty try node. And then I'm going to move to that node, and I'm going to increment the count of that node by 1, because right now we are inserting a word. And then I also have a count method. Let me show you how this count method is going to be used. Down here, I have my result. I have my root try. And then I go through every word in that list, except I go through the list in reverse order, because that's how we're counting it. For every word, we want to just check all the previous words, or rather all the words to the right of it. So first, what I do is I count. I make sure to count before I add the word, because if I don't do that, then I'm going to end up having a duplicate count. I'm going to end up counting that word, because if I insert a word, of course, the count is going to return a positive number. Technically, a word is a prefix and suffix of itself. So that's what we're trying to avoid. That's why I make sure to count that given word before I add that word to the data structure. So count is implemented pretty simply, similar to what we have up above. I again go through the word and the reversal of the word at the same time. I check if it hasn't been inserted. Well, then we can just immediately return 0. Otherwise, I move to that node, and then by the end, I will return the count associated with the last node. So this is the readable solution. I will run it for you, and I would say it's pretty efficient. In terms of big O, it is pretty efficient. Of course, the runtime is going to be worse than somebody like Lee's solution, who wrote things in a very, very concise way. If I were to run this, it'll probably be more efficient. Let me just actually try that right now. Yes, you can see his solution is definitely more efficient in terms of the real runtime, but if you actually compare the raw numbers, it's only like twice as efficient. So really, that doesn't make a huge difference. But anyways, let me see if we can simplify this a tiny bit. If I were to here, rather than having a count method, I think from here, the add method, we could just return the count associated with the last node. But we're going to have a positive 1 there in any case. So I think we could return the count and then -1 from
self.map. I just kind of want to understand this properly. So we need to create self.root is equal to try node. All right. We need a add method. We need
I'm not 100% sure. I'm just doing this on the fly. Let's see if that ends up working. I can just move this over here and then try that. And yes, it actually does look like that solution works, and it did make things marginally more efficient. I don't know what you guys know, but his solution is pretty efficient. Of course, the right can just immediately return 0.
okay, we add here. We create a pointer to our root. Cur is equal to self.root. Right, we loop through the beginning and the end of a word, right? And we use zip to do that. Reverse W. I'm not really familiar with zip in Python. Okay. Reverse W. We check, okay, if C1, C2, not in, I guess we should probably make this children. Not children. Turn 0. Not in cur.children. We want to add it, yeah. Cur.children. C1, C2. Alright, is equal to try node. Cur.children. C1, C2. We move. This moves, right? Moves to next node. Cur.count plus equal to 1. Why are we counting here though? Where's W? We loop through Check if it's in the hash map. Not in code.children. We return 0. Otherwise,
Otherwise, I move to that node, and then by the end, I will return the count associated with the last node. So this is the...
oh, whoops, this is not meant to be in here. Whoops. Root as you gonna try. We would loop through for W in reversed words. Res plus equal to root.count W. Root.add W. 10 res. Trying to understand. Oh, they're separate classes. That's tree. Bro, this is... I kind of understand what is going on here, but I definitely... Data structure is tough, bro. For W in reversed words. Like, bro, I just... I think this is too much of a problem, bro. I need to go to something more basic. Trees, backtracking, heap priority queue graphs, 1DP, advanced graphs. Intervals, greedy. Yeah, like we're kind of in, probably excluding advanced graphs, probably in here. You know, learning here. Done trees, so probably, yeah, in here. Implement a tree, prefix tree design, and add search words, data structure, word search too. Like, simple as DS I've learned. Man. Intervals, dude. Heap priority queue. Let's check out, let's do a couple of these. Design Twitter. It's a good one. Backtracking trees, backtracking, heap priority queue. Yeah. Graph problems are tough, bro. Like, let's do a heap priority queue. Let's check out like last stone weight or something. I think heaps are easier. Like trees are tough to like think about, bro. Like, okay. You're given an array of integers stones where stone's I is the weight of the ith stone. We are playing a game with the stones. On each turn, we choose the heaviest two stones and smash them together. Suppose the heaviest two stones have weights x and y with x. Result of this smashes. If x is equal to y, both stones are destroyed. And if x is not equal to y, the stone of weight x is destroyed, and the stone of weight y has a new weight of y minus x. At the end of the game, there is at most one stone left. The stones left return 0. Okay. Okay. Stones.heapify. Print stones. Let's print stones before as well. Has no attribute heapify. Oh shit, we have to import heapq. Import heapq Python. Oh man, jeez. This has no attribute heapify. How the hell do you heapify something? Heapq.heapify. Heapq.heapify stones. We got 274, which is what the input is, and then when we heapify it, we get 1127. We get a min heap, right? So creates a min heap, right? What do we want to do? We want to give an array of integer stones where stones I is the weight of the ith stone. We're playing a game with stones. On each turn, we choose the heaviest 2 stones and smash them together. So we have to pick 2 stones and smash them together to make 1 stone. Okay. So I'm thinking maybe we... So for our first case, we take 2 stones, right? Where's that documentation? We take the 2 stones, we heap q.n largest, right? Heap q.n largest, and we take 2, we pass in our iterable, which is our stones, right? Let's print our stones. We take the next 2 and we print our... I think they give us like an array of some sort. Let's just do array. We get 8 and 7, right? The 2 largest, okay? Well, maybe we can take these 2 stones, put it back in our heap queue. Combine 7 and 8 to get 1, so the array converts to... Okay, so they do put it back in. They go 2, 4, they take 7 and 8, and they put 1 back in. Then they take the next 2. We combine 2 and 4 to get 2, so the array converts to 2, 1, 1, and they take 1. Okay. Okay. So what I'm thinking here is we go, okay, well... we need to make some loop that'll keep going until... Star does not equal... Okay, wow. Does not equal 1. I don't know if that's the right thing to do, but... Again, I think it comes back to the point where you're comparing the length of something and it's constantly changing. We take that, we do, okay, well... Let's do x is equal to array 0, y is equal to array 1, And then we do, okay, if x does not equal y, we do well, because the top value is always going to be greater, right? So we would do the absolute value of y minus x. And is equal to the absolute value of y minus x. Right, and then we just put that. We put that in. So we would do, okay, well, back to our heap push. Heap q dot heap push. Dot heap push ands. Right? Else, I mean, if it's not there, we don't really do anything with it, right? We technically pop it, right? And we just go to the next one. Which I think should be good. And then at the end of the game, there is at most one stone left. Turn the weight of the last remaining stone. If there are no stones left, return 0. Stones does not equal 0. Then we would just return. We would return our stones 0 if none else. We just return 0. Heap push. Shit, what is it? Heap item. Okay, so I think it's stone. Hands. It's definitely our while loop here. Um, yeah, why did I do that? Well, length of stones is greater than 1. Jeez, am I that stupid? Like, the length of stones is greater than 1. Time limit exceeded. I getting a TLE? Okay. I'm getting a TLE because apparently of this, that it's O of N. I highly doubt that. What did I just do, bro? This is not using a heap, dude. I want. Okay, so they possible negative values into them in here. Okay, so they make a max heap. Okay. So maybe that must be the move here instead of doing this, right? So, okay. Let's create a max heap. Let's do max heap. The X for X in range stones. Okay, let's get rid of this bullshit. Actually, we can probably keep this stuff. X, negative X for X in stones. 2, 7, 4, -1, 8, -1. Okay. Now we can do, okay, max underscore heap dot heapify. Let's print out max heap. And we'll print out max heap here. There's no attribute heapify. Okay, is it heap key dot heapify max heap? That's what it must be. Okay, nice. Now we want to loop through while our stones are greater than 1. We can get rid of this. We can do heap pop, heap q dot heap pop heap. Pops the smallest item from the heap. Yes, sir. Yes, sir. X is equal to this. Y is equal to this. And if X does not equal Y, we do, okay, our AND is equal to the absolute value. We don't want the absolute value anymore because that's going to return us a positive. Push it back onto our heap. So we're going to do, well, okay, I think we'd have to do, well, the absolute value of Y minus the absolute value of X, which will return us a positive. And then we just put in negative ANDs. We return stones 0 if stones does not equal null, else 0. expected max heap 0 if max underscore heap. Heap is not defined. Oh. Max underscore heap. Heap. Index is out of range. Why are we getting an index that's out of range? Oh, wait. Yeah, it's because we got length stones here. We want to do while length max heap. Else 0. Output 0, expected 1. What am I missing here? Getting an output of 0, but we're expecting 1. Back into the original stones. Oh. There we go. Oh, wrong answer. -2. I think when we're doing the absolute value, maybe it's messing it up. Y minus x. Let's do x equal to negative, because 2 negatives make a positive. We push the negative. We take back the negative. Man, I don't know. The -1 here. We've got a negative, a negative. We're popping a positive. We're doing this. Maybe this needs to still be the abs, because then we're getting a negative. Okay. Could that be? Okay, there we go. We're just missing the absolute value. Okay. What did they say here it was? When you pop x1, you correctly negate them to get the original. However, when you... Okay. Nice. We're going to take a look at some more problems. About an hour in. I got to go to the bathroom. But we will take a look. Let's take a look at the kth largest element in an array. We'll take a look at this one next. But I'll be back. I got to go to the bathroom. I'll be back in a couple of minutes. What's up, guys? We're back. I'm going to take a look at the next one. Kth largest element in an array. Another heap problem. Let's take a look. Kth largest element in an array. I got a medium problem here. Array divided by sort of heap priority queue. Whatever. Okay. Given an integer array nums and an integer k, return the kth largest element in the array. I want the second largest one. Note that it's the kth largest element. Can you solve it without sorting? Well, yeah, we can, right? So, I think this is a pretty straightforward problem when we import our heap, right? We create, we obviously want a max heap, technically, right? Let's see if we can do it using a min heap, because I think we can. I think if we just loop through all the values, let me try. Okay, let's do, okay, min heap is equal to, heap q dot heapify nums. Let's print out min heap. Make sure that it did it. Okay. Heap q dot heapify nums. Why is it not printing, dude? I don't know. Oh, it's because we have nothing in our max heap. That's why, bro. Oh my gosh. Okay. Min heap is equal to nums. No, that's not how it is, right? How do you copy it, bro? Like, what? How to another array Python. Jeez, man, use the copy method. Okay, alright, we'll just do that. Equal to nums.copy. Still not printing anything. Bro, what is going on right now? I mean, we can always just do x for x in nums. That doesn't work either, bro. What is going on, dude? Oh my god, dude. Heap q heapify the heap q dot heapify function modifies the list in place and returns none, so you're assigning it its return value to be min heap. Oh shit, forgot to do. Okay, there we go. Okay, we heapified it, right? So now we pretty much want to loop through, well, while the length of the min heap is greater than 2, greater than k. So and is equal to what is the heap in Python? What is it? It's heap pop. Heap q dot heap pop heap. And is equal to heap q dot heap pop min heap, right? We just return ands, right? I think it should return the last one. We return 4, but we want to return 5, so let's say greater than k minus 1. Maybe it'll print now. There we go. There we go. There we go, bro. Easy problem. Okay. Let's take a look. We'll do more heap problems tomorrow. I definitely want to start understanding it, try a little more. I feel like it's tough though, like one-dimensional DP. Our advanced graphs, we got our greedies, we got our intervals. Design, add, and search words, data structure. Design, add, and search words, data structure. I want to call it here after this one, I think. Design a data structure that supports adding new words and finding if a string matches any previously added string. Implement the word dictionary class. Okay. Void add search word. Adds word to the data structure. It can be matched later. Bool search word returns true if there is any string in the data structure that matches word, or false otherwise. Word may contain dot, where dots can be matched with any letter. Children. We want like a little map, right? And then we want to do self dot end word is equal to false. we want to be able to add a word, right? Self dot, oh wait, cur is equal to self dot I feel like we're gonna make a tree node class though. Define, add and search words, data structure.
Did you know you can AFK Bloods and Zaya whilst learning to code in Python? Go to boot.dev. We've known our students to pull it off. Here's how. Monitor 1. Code.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve design, add, and search words data structure. So this is another problem from the blind 75 Leetcode problems list. So this is the spreadsheet I've been using to track which videos we've uploaded for those 75 problems. You can see that most of the solutions have already been updated, and today we are working on this problem, a tree problem, add and search word. So basically another day, another problem from this Leetcode blind 75 list. The link to this sheet will be in the description if you do want to take a look. So basically we're designing a data structure to efficiently solve this problem of basically adding words. We're taking new words, adding them to the data structure, and also we're being given words and we want to search to see if those words match any previously added words to our data structure. So we only need to support 3 functions for this data structure. One is just going to be the constructor that's going to initialize the object. One is going to be adding a word, and that one is pretty self-explanatory. So we're just given a string, a word, and then we're adding it to the data structure. Now this word could only consist of lowercase characters from lowercase a to lowercase z. And the third one is going to be the one where the bulk of the algorithm is going to be contained. So this is going to be the searching words. So we're searching a word, and the word can contain any character from lowercase a to lowercase z, but there's one additional character it could contain, a dot character. And what we're told is that the dot character is actually like a wild card. It can basically match any character in the string. So for example, let's say in our word list so far, let's say we had just a string A, B, right? So this is what we have so far, and we're trying to search dot B. So basically, would this search match any words that contain so far in our data structure? Like a wild card, it can basically match any character in the string. So for example, let's say in our word list so far, let's say we had just a string A, B, right? So this is what we have so far, and we're trying to search dot B. So basically, would this search match any words that contain so far in our data structure? The answer is yes, because the dot would match any first character, right? So that we basically match this lowercase a, and then we do have an additional b which matches the second character in the string. So a dot matches any character. That's what's going to be tricky for us to implement. Now the brute force way to solve this problem is pretty simple, right? We would basically have a list of words, and then just for every search, we would just say, okay, does this search match any of the words in the input list? Now, that's not going to be super efficient. A more efficient solution is going to require a trie data structure, aka a prefix tree. So this is what we're going to be using to solve this problem efficiently. I will say, if you've never heard of this data structure or you've never implemented it before, you basically don't have a chance of solving this problem efficiently. But if you have heard of this data structure, it's pretty intuitive why this data structure is used in this problem. Basically, you know, a prefix tree, right? So for example, if we were searching b dot dot, we would want to first find all words that start with the character b, and then check, you know, are there any of them of length 2, because the remaining portion of this can match any string of length 2. So a trie is basically a tree that has some kind of root node, and each node can have up to 26 children in this example, because we have lowercase characters from A to Z. So basically each node is going to represent a single character, right? And then each node could have up to 26 additional children. And basically a word in this case, for example, this is A. If I had a B here and then another C, this is going to be a single word, right? And so if we inserted the word, let's say we added the word ABC into our try, this is basically how it would look like. Now, one additional thing we have to say is for a particular node such as C, we have to say this is the end of the word, right? Because what we're trying to say is we did not add the word A, we did not add the word AB, we've only added the word ABC, so we have to designate that this is the last character. Now, if we added another word, for example, AB, what we're going to do, we're not just going to repeat that. We're not just going to say, okay, now there's going to be a lowercase a here, then there's going to be a lowercase b. Notice how we already have those characters available to us. We're going to reuse these characters. So instead, what we would do, adding this word, we would say, okay, let's add an A. So let's start at the root, add an A. We see there's already an A that exists. Then we'd say, okay, from here, let's add a B. We see that a B already exists. So once we get to the end of the word, right, that was the last character, then we would just say, okay, designate this as an additional end of the word. So now we have two words along this path. We have one word AB, we have another word ABC. Notice how all words starting with an A are going to be here, right? We could have other words, maybe a T or something, right? And other words as well, right? Basically, all words that start with A are going to be here. That's what makes this efficient. That's why this is called a prefix tree, because let's say we wanted all words starting with, let's say we were searching something like this, right? We're searching A, B, ... So we want all words, for example, or even one word of length 5 that starts with A, B. Then we'd go, okay, let's find A, then find B right here. And then we'd go through all possible children that it has, right, in the tree. We would do a brute force depth first search, backtracking type approach, and then we'd get a word. We would try to find a word like this one. So with that being said, let's run through the example. You can see at the above, the first word that we're going to be adding is bad. So let's add a character for B. Let's add a child for this A. Let's add a child for it D. So now we have inserted the word bad. We do want to designate this as the end of a word, so I'll just mark it blue, but in our code, obviously we're going to do something different. Next, we're adding another word, dad. So we have to start along a different path because we're going to search for a word pad. Now, so what we're going to do is we're going to start at the beginning, right? Are there any words pad in this? So first we're going to try, are there any P's? We're going to look, is there a P? We don't see any, right? We only have B, D, and M. So we don't have any words starting with a P. That means immediately we know false. Pad does not exist in our input.
We initialize our self.root is equal to tree node. Do an add word function. So an add word would go, okay, cur is equal to self.root for char in word, right? We want to check, okay, if char not in cur.children, then we want to add it, right? So we would do, okay, how we at it? Is it char.children, right? Yeah, cur, that's what I meant. Sorry, not char. Cur.children. Char. Char is equal to char. Right? Is equal to tree node. Cur is equal to cur.children. Children char. What do we do if there is one? Do we just go to the next value, right? Then we need to somehow check if it's the last value, right? So yeah, that's right. We leave the 4. We leave this 4 and we can cur dot cur dot end word is equal to true. Right? Because where we'd be at the last value, right? Of true to tree node, right? And as we search through, we go, well, for char in word, want to make our cur pointer, so cur is equal to self.root, char in word, if char not in cur.children, we would instantly return false, right? Otherwise, we keep looping through and we go, okay, well, cur is equal to cur.children char. We loop there and then we check, okay. We return cur.endword. Yeah, because we'd always return true, right? Because it's a boolean. Return cur.endword. Not in cur.children. Oh, well, we need to implement the dot, right? So how do we implement the dot? That's what we're missing here. Well, how would we implement the dot? We'd need some sort of like else if or something. Else if char Alright, equal to dot. We need to do something.
That's why in the output over here, you can see false is what's returned. Next, we're searching another word. That word is going to be bad. So we're going to start at the root and see, are there any B's? We're going to see that, yes, we do have a B over here. The next character in the string is A. So does this B have a child A? Yes, it does. It has an A over here. The last character is a D. Does this A have a child D? Yes, it does. It's over here. Now, we found the characters we needed, but now lastly, we have to say, okay, the last character that in the searching word is D. Is this in our try? Is this designated as the end of a word? Since it's marked blue, it is. Therefore, we're going to return true for this input searching word. And you can see that's what's written in the output. This returns true. Let's go through the last two search examples. So in this example, we have dot AD. So what does that mean? Remember, the dot character means we can match any character. So we're going to start at the root and we're going to go down all three paths or literally any of the paths. And to do that, we're going to have to use depth first search, or basically a backtracking approach, right? And remember, we're only looking for one word that matches this, right? So let's say the first path we decide to go down is this one, right? So this is a B, and we're allowed to use a B because the dot matches any character. So this matches so far, right? Next, we're at the next character, A. Does this path have a child A? Yes, it does. So we found another match. Next, we're looking for a D. Does this have a child D? Yes, it does, and it's designated as the end of a word. So in this case, we found one word that matches this, and that's all we need. We just need one word, so we are going to return true, and you can see that up above. Now, if this one did not match, for example, if this wasn't designated as the end of a word, or maybe this was instead an X character, we would say, okay, we didn't find a match down this path, but it doesn't matter because remember, the dot matches any character, so we don't have to go down this path. Let's try going down this path, right? And we would do the same thing. We'd say, okay, we have an A, we have a D, that means we found a match, that means we can return true. And you can see that this is not going to be super efficient, right? We would have to go through every single character that's in our try decision tree. But it's still more efficient than a brute force approach, especially for this last example. So we're doing one last search, and in this search we start with a B, but then we have two dot characters. And the reason this is more efficient with a try rather than just brute forcing every list, because this at least tells us, okay, we're starting with a B, so what we're going to do in our try decision trees, we're going to say, okay, every other word that starts with any other character than a B, we're not going to consider them. And we have a pretty small try right now, but it's possible we could have a really big one, right? So what this does for us is it eliminates a lot of the possibilities. We say, okay, at least we know we're starting with a B, and yes, we did find a matching B. So we can go down this path. Now we get to the brute force portion where we have a dot, right? So basically, in this case, it's simple because we only have one child, but maybe we'd have multiple, and then we'd have to go down all of those paths. But in this case, it's simple, right? Let's just check. Do we have any characters that go below it? Yes, any character will match this first dot. Now we're looking for another second dot. Do we have any characters that match it? Yes, we have a D, and it's the end of a word. So yes, in this case, we also found a match, so we can return true, just like we have up above. So once you can kind of understand this visual example, it's not super hard. Now it's time to actually implement the code, and I'll admit that it's actually a little tricky, but I'll try to guide you through it. So one thing...
Step back, back it up, back it up, back it up.
thing I like to do for try problems is just define a try node, because it's going to have a couple variables. So in the constructor, we're basically going to initialize two fields. So for this try node, we are going to have a list of children. Now I'm going to use a hash map for that. So basically what I'm going to say is for each character, we're going to say something like, A is mapped to a try node, and we could possibly do that for every lowercase character from A to Z. And for every character, we also need to designate if it's the end of a word. So I'm just going to use a Boolean for that, call it word, and initially we'll set it to false. And so basically the only thing we need to do for the constructor of the word dictionary is just define a root. So let's call it root, and it'll just be a try node. So initially you can see that we don't have any characters inserted, right? We just have an initial empty try node. It doesn't have any children, so no characters are inserted. Next, we are going to do the add word portion. This portion isn't too difficult. So what we're going to do is we'll set current equal to what our root is. So self.root is where we're going to start. And what we're going to do is basically go through every single character in the word. And what we're going to do is we're going to check if this character is not already inserted, because it's possible this character could already be inserted in the try. So we're going to check if C is not in current dot children of the current node's children. If C is not in there, then we need to obviously insert it, right? So what we would do is say current dot children of C is going to be a new try node, where we inserted a try node corresponding to the character C. And then of course what we're going to do is we're going to update our current pointer to this new try node. If it didn't already exist, that means we just created it. If it did already exist, then we just shifted over to it, right? What we're ultimately trying to do is insert every character from this word into our try. And once that's been completed, what we're going to do at the end is say, okay, current dot word is now going to be set to true. So we have created the characters and designated this as a word. Okay, now for the actual meat and potatoes of this problem. And this part is actually going to be recursive, and let me show you why before we actually start doing the recursive portion. So this is going to start similar to what we had before, right? So current is going to be initially set to, let's say, self.root, right? And then what we would want to do is go through every single character in the word. In this case, I'm actually going to use the index of the word, and you'll see why in a moment. So for I in range length of the word, and then we're going to get the character at position I, so word of I. And so remember, this character could be any character from A to Z, in which case the problem would be straightforward, right? We would just search our try and see, does this character already exist? And then we'd continue. If it doesn't already exist, then we would return false. But we know this character could actually be a dot character. That's what's going to make this tricky. So if C equals a dot character, the else condition is if it is a regular character. Now let's start with the else case because it's a little more simple. So if C is just a regular character, what are we going to do? We're going to check if C is not in current.children. That means this character does not exist. We needed this character to exist. We're searching for this word, but this character does not exist. So what do we do then? Well, simply we can just return false. That means we know for sure this word does not exist. If it does exist, then obviously we're going to shift our current pointer to that node. So we're going to go to current.children at character C. And then we would just continue our algorithm, right? But in this case,
well, we've pretty much got the same thing here. So we need to access the for char in range length word. We check, okay. Char is equal to this. We do something else. We want to check, well, if char not in cur.children char not in cur.children, then we can simply just return false. Otherwise we move this value over here, right? Yeah. Char is equal to word char. If char is equal to dot, right, then what do we want to do? We probably want to loop through children, right? So we go, okay, well, we go, well, for, let's call it neighbor. Thinking about graph problems in cur.children. For neighbor in cur.children. A neighbor in cur.children. I think we gotta loop through all the stuff, right? You said it was a backtracking approach, so if we loop through the children.
This is going to be a little bit more tricky because remember, if the character is a dot, that means potentially we're going down 26 different paths because this dot could match any of the 26 characters. And we can't really do that iteratively very easily, right? We are going to use backtracking or recursion to help us do that. So for example, let's say we had a string like dot AB. What we would want to do then is say, okay, dot, it could match any of the possible characters. So what we would say then is we would go through for every child in current.children.values, because remember, for current.children, that's a hash map, and then we want only the values because those are going to be the actual children. So because we know the dot could match any character, so for this dot we would basically match every single character, and then we'd say, okay, for each of these we want to do the recursion on it, so we want to do the depth first search on this. And when we're actually doing that depth first search, it could just be an iterative matching. So what I'm trying to get at is that this entire thing that we just wrote is the recursive function. This is the depth first search, right? We have the iterative portion here where we don't have a dot, and we have the recursive portion over here where we do have a dot. So let's wrap this entire thing inside of a depth first search function. Depth first search, DFS, and so let's just tab it over. So now let's think about it. When we're doing our depth first search, what are we going to pass in? And well, we want to know what's the remaining portion of the word that we are trying to match, right? So we would want to pass in the index. So let's call that J. We're passing in the starting index J, right? And the other thing we're passing is what's the current root or the current node in our trie that we're at. So in this case, so depending on which one of these we're iterating through, we're going to pass in that child node, right? So that's what the node that we're going to be passing in, whatever child that is. So that's how we're going to call DFS. So let's define that up above. So J is going to be the index parameter, and let's call root what the node that we're passing in is. So okay, so current is, instead of being called self.root, it's actually going to be initialized to the root that we end up passing in. And okay, so here I passed in J, but what we would actually pass in is going to be I. Actually, not just I, but I plus 1, because we're going down a child. So we're going to pass in I plus 1 as the index of the character that we're looking for, right? Because because what we're saying is we're skipping the dot, so we're going to have to increment I plus 1. And this function is going to return a Boolean. So if this function ends up returning true, that means we found one path that matches. And remember, if we find a path that matches, we return true immediately. We're done. Done. We don't have to do anything else. If we don't find a path, we're going to keep going down all possible paths until we do. If we never find a true, if we never find a match, then we're going to return false. Oh, and one more thing. So initially up above, we said I is going to go through range of the length of the word, but we know we could be starting at a different position. Here, we're always going to start at 0. We don't want to do that. We always want to start at J, whatever it happens to be. So that is the main recursive portion. And the last thing is, let's say we were given a word ABC, and let's say we found a match, right? We didn't have any dots in here. What would that do? Well, we'd go through the for loop, we'd always execute the else condition, and we would always find the current node, and then the entire loop would be finished. Then what would we want to return out here? Well, we would want to return whatever current happens to be. So if current.word is true, then we would return true. If current.word was false, then we would return false. So we can just leave this as it is. So that's the main portion of this algorithm. The last, as you can see, this function did work, and it does work pretty.
Return code.end word. We want to return keep as 0 self.root. Child is not defined. I meant neighbor. Neighbor. This is definitely a tough function, bro. Like, okay. Damn, what a tough problem. Okay, we're gonna call it for today. Appreciate you guys watching. We got a few things to do before I got work, so you know, starting to understand trees a little bit better. I think heaps are pretty easy. I mean, they're pretty straightforward, but it's just like, you know, my mind messing with trees, you know, is a little tougher, but we'll figure it out. We'll get to it every day, and we'll keep going. So appreciate you guys watching. I will see you tomorrow.